IIT Patna. We welcome Dr. Ranjan Kumar Behra, who is currently an associate professor at the Electrical Engineering Department of IIT Patna. Under his umbrella of research, various topics such as design and fabrication of power electronic circuit, control of electric drives, application of non-linear control theory to power electronics and electric drive, pulse width modulation technique for power electronics is covered. The determination showed by Professor Ranjan Kumar Behra has led to 25 journal papers and 65 conference papers. As a result, his overall citation is of 706 and H index is of 12. Apart from this, he has I-10 index of 14. Under his incredible supervision, many students have completed their doctoral degree and master's degree. Additionally, he has one book and two patents in his name. There are various awards and achievements of Professor Ranjan Kumar Behra to be penned down. Now, humbly, I would like to ask Professor Ranjan Kumar Behra, sir, to start with his expert session.
Thank you, sir. Thank you very much.
Most welcome, sir.
So, good morning, everyone, and I special thanks to Yogesh sir for inviting me for this session. And today I'll speak about the advanced power converter control for wind and solar. And initially we will see some of the fundamentals of wind, as all of you know that fundamental. But most of the time in India, we are not using the permanent magnet motor. Where I was working in the General Electric, so that time we installed nearly 500 megawatt wind converters, wind turbine generators, PMSC based generators, and a synchronous machine also they utilized at that time. So I will speak this both the thing, and we have also completed many projects in the different place in Bihar and also in Port Blair. So that I'll try to discuss if time permits. So today is we will discuss the modeling, control, design of permanent magnet based motor, because in a high power range, the permanent magnet motors are better as compared to double fed and synchronous generators. What is there about it? Then we will discuss some of the grid connected current source inverter fed PVs, and then different type of generators. Then we will discuss some installation projects. So permanent, these are the power converter topology where we use different kind of what are the input and then transmission, then what are the type of generator or machine we use, then what kind of rotor and starter, and whether isolated one or grid connected one. So I'll discuss both grid connected one as well as the isolated one. And we will discuss what research we can do in this field, and because then what are the output. If you see multi-megawatt, I am not speaking about 5 kilowatt, 2 kilowatt, it is multi-megawatt. And megawatt, I remember we installed 2 megawatt wind turbine in Hong Kong, and that was so huge actually. Sometime I have seen the truck, very big length, that also it will be shorter for their blades. So this multi-megawatt wind turbine, there are three types. double fed induction generator, squirrel cage, and a synchronous generator, whether permanent or with excitation. So if you see that today in 3 megawatt range, there are three generators in the large wind turbine. One is DFIG. If you see this, most important today is that because government is giving us that your wind power or wind generator must be connected to the grid. If you don't connect suddenly, if there is a some abnormality and you disconnect the grid, suddenly complete system will be oscillating in nature, and it will give. That's why we have most important performance is ride through voltage ride through, low voltage ride through performance is one of the basic requirement today. So if you see here, direct drive, DD means direct drive, synchronous generator, and direct drive PMSG, permanent magnet synchronous generator, they both have that capability. That's why people want, because else the government, for example, in the Europe, the government is completely without this right through performance. You cannot connect your wind turbine to the grid. So that is very important thing today in the according to the standards of European countries. So this permanent magnet, if you see that the losses are very less, okay, and but in terms of cost, weight, size, DFI has advantages, but it is most unstable kind of generator, okay, and you required sometime the crowbar protection, many kind of protection system. And reliability also associated because of the slip ring and brushes, the reliability is very less. Actually, if you put a 1 megawatt DFIG and if the brushes fail sometime because of the centrifugal force is not balanced always. You know, the all these blades are connected and the blades they are rotating. So sometimes the wind is not laminar wind. So sometimes turbulent wind will create vibration of this blade, so that the blade entire body structure will start vibrating. So when the entire body will vibrate, because such a huge mechanical structure, when it vibrate, there will be heavy, the ball bearing, everything they started developing lot of heat. And so also sometime I remember we put a squirrel cage around 250 kilowatt generator, and just we put everything, and there was four two-stage gear ratio, and suddenly the because of this mechanical vibration, and there is some because of the unbalance in the mechanical structure, sometimes it struck with the wire, and completely that generator started burning actually. So we cannot understand why it has happened, because we put all insulation, all insulating wires, everything we put, how it is happening. And that is sometimes it is also very difficult when to find out the problems which will happen around 50 feet, 30 feet above. It's very difficult. There are some difficulties in providing ride-through capability to DFIG, and then multiple machines today, PMSG, are very people are trying. They are developing multiple. Why? Because when the wind speed is very small, this multiple drives, they will actually the permanent magnet motor drive, if you have number of poles, so number of poles means your power output. It is like a connecting small batteries in the series. So pole number is more, then you can each pole with low speed also you will get power, so that power can be bring back and can be transformed into the grid. Raw power can be connected to the pure power also. So that's why there are many manufacturers now they are trying, and also two these multiple machines are already installed, and that is around 600 kilowatt machines, and one is in Poland. They established one in USA. So there and in China there are two three they have installed. And that's why the direct drive generator is the noise reduction can be achieved by when you eliminate sometimes the gears. So there is a multi-breed concept is that when this multi-breed is composed of medium speed permanent synchronous generator and a single series gearbox. Okay, the gear ratio is about 6 to 10, and it was introduced by a company called Arriva, and this allows reducing the weight and size of the generator combined, and they are lighter and more reliable, cheaper than the standard three-stage gearbox. Okay, and this is very popular, and you can see here a comparison of the generators. If you see the PMSG single stage is just a 25% direct drive PMSG, and you see single stage this gearbox, it is only 25%. So you can reduce 75% of the weight, and cost also 5%, and power loss is little higher because of the because your when you are designing your speed of the you need to develop the number of poles that need to be reduced, so that the speed can be according to the standard of our reference speed. So there are also a large 10 megawatt also developed by the company. There are many manufacturers in the world, and there are Alstom, Clipper, Dewwind, and in if you see here, what technology power converter they use, that back-to-back IGBT, low voltage. Okay, so IGBT B2B means back-to-back converter, and IGBT, integrated gate bipolar transistor and low voltage. Okay, so power level you can see they have developed up to 3 megawatt. Doson ENO energy also around 2. It is synchronous. Different companies they develop different kinds of wind turbines, and in India we use the most is we use some because most of our wind turbines are the double fed and cage rotor, so we use this Suzlon. Okay, if you go to most of the Maharashtra and Gujarat, and also Vestas also we use, and now G also they have a few turbines they are trying to establish. So anyway, there are these companies. So this power processing topology applied. You see here, there are permanent magnet synchronous generator, and connecting to 3 control switch and 3 uncontrolled switch. So this is very simple, and you have 3 active switches, and you can easily control 3 switches means very easily simple controller you can design. And the short circuit through the leg is not possible, and high efficiency due to reduced number of elements, because there is no switching loss, And that is why this type of topology are few places it was developed. And power processing topology, and by using two back-to-back bidirectional converter. Okay, you have permanent magnet synchronous generator, interior permanent magnet, and then by using some filter and DC link, and you can feed back to the grid connected system. So this was very popular. Actually, now also this is popular. And there are also Bin Wu is a professor in our uh, Ryerson University, Canada. He developed a topology like this, that you have a permanent magnet, then you have the star multi-winding transformer, and multi-winding transformer they can convert from AC to DC by using rectifier circuit, so that the cost of the input converter is reduced, a simple rectifier circuit, and charged to this DC link. Okay. So, but there is just some problem in this one because of the circulating current. Okay. So then it is connected to PWM converters and then fed to the grid. Okay. So there are 12 pulse rectifier circuit like we use in the power quality conditioner, and you can change this one. So there are a lot of advantage, low cost and high reliability, because there is no, in this input side is a simple diode converter. So when we do such things, when we will go for a higher power, we need to have not a two-level converter. You should go for the multi-level. So up to 25 kilowatt, you can design a two-level AC-DC or DC-AC converter. But when you go above 25 kilowatt, okay, actually generally above 10 kilowatt, they use a parallel and series combination of the converter like that. But 25 kilowatt is the, so above that one, we prefer the multi-level converter, because the two switches are connected in series, which makes to distribute the half of the blocking voltage. So that is why the blocking voltage limit increases. And second thing is the low switching frequency, you will get same type of performance, like total harmonic distortion performance, with a lower switching, switching frequency. So low switching frequency means losses also will you have a very low loss. Okay. So like that, when this wind turbine is connected through permanent magnet, and you have a three-level neutral point clamped converter, and you have a two DC link voltage, and then you have a three-level NPC converter and connecting to the grid. Okay. So you can connect to the grid by putting directly or by using isolation transformer, but we have taken here, it is a simple grid. So when we go for this one, first we model this permanent magnet generator side converter structure. And when we model it in the DQ transform, many mathematical equations are there, but I just put the primary equations which we required for our control algorithm. So this is ID, IQ, and this is a simple state space analysis. And then we have two DC link voltages, VDC1 and VDC2. And when we derive this one, you can see that here it is a simple two equation, and these two equations are required when you want to, if there is an unbalance in the DC link capacitor, you need this equation for that. And for controlling also. So this current control, if you see here, It's simple because it is a permanent magnet. So this is a simple equation. And these equations are, you design the controller, PI controller by using this one, okay, VDC and VDC star integrating VDC. Star minus the reference voltage minus the actual voltage. So if you model the permanent magnet generator, you can see a simple equations where it is very simple and torque is directly proportional to Q axis current. So when we simulated, you can see here, these results are very, very important analysis to understand the performance. First thing is, when you connect to the grid, you want that it should operate, or the grid side converter must operate utility friendly, so that both the power you are feeding to the grid, it must be sinusoidal, and both the current and voltage must be unity power factor, so that the reactive demand by this must be zero. So you may ask, there is some magnetizing component because of the winding or something. So how that one? So the small capacitor in the dish link that can supply that small, very negligible amount in case of in multi-megawatt machines. So anyway, this when you use power converter, then require the power quality actually. So when you operate at a unity power factor, both current and voltage, you can see that it has your maximum power as well as good power. You can say that it is utility friendly. But you can see it is a wind turbine. You can see here, because it is a wind turbine, it is associated with mechanical vibration, electrical vibration, torsional torque, and with this vibration, the rotor has some kind of vibration also. So when the generator you are getting the power, because the rotor is having some vibration, you can see that the current is not constant. Although you can see that the voltage is constant, the current is associated with the dynamics of that inertia. So that current is, you can see that it is sometimes high and low. So this is the exactly model of a wind turbine associated with the field, because field there are a lot of wind, and sometimes wind is very laminar, sometimes wind is very turbulent. So the turbulent wind, so that time, most of the time when the turbulent wind start coming, it will directly shake the entire body also. So that is why, because it is a big mass. So this is the exactly, you can, the current is reflected in the in this. So this is our three level. You can see that in the three level, you can see that every, you can see the voltage waveform. It is very beautiful. If you analyze here, sometimes there are high frequency, you can see that very higher frequency switching, sometimes very low frequency switching. And it is due to that only. It is due to this. You can see that this is also, you are seeing the, and this is the current. Okay, the green one is the current, and this is a three level output. Okay, line to line. Now this is a small simulation we carried out for 10 seconds, and this was the wind speed and RPM. It started increasing, and this you can see that because we put this is direct the torque control, so easily you can see that it is the tracking the shape of your wind turbine. So generally, there are delays also associated because it is a simulated result, but in practical system, always there is association of delay. Delay is due to your converter delay. Delay due to your, for example, A to D converter, analog to digital converter. If you see a typical analog to digital converter, you will find there is a delay of 1.1 microsecond to 1.8 microsecond, depend on the, for example, ST microelectronic. There is a delay of 1.6 microsecond. Mitsubishi, it is 1.2 microsecond. It depends on the company which manufactures that A to D converter. So here also it is associated with that one, but the overall performance remains the same as it is shown here. Now, if you see here, the DC link voltage is not actually, they both are not constant and not balanced. So there is a unbalance because of, you know that inherently, I told you, inherently there will be this voltage are unbalanced because of your mechanical as well as a different current it inject to your DC link capacitors. So this we need to control this one from the input side, not from generator side. From grid side, you can control this, or you can use some kind of chopper circuit where it can the chopper can force this DC link capacitor to charge and discharge immediately, so that you can maintain the constant and balanced voltage. So we used the chopper circuit. So when we used the chopper circuit, you can see that both the DC link voltage are maintaining constant actually. And there is a ripple because you cannot, if you are an engineer, you can, nobody can say that that you have a DC link capacitor and you are getting constant one straight line. No. If somebody gets a straight line voltage, then that is wrong actually. Because as an engineer, nobody will accept, because this is a, there must be a ripple. So this is our voltage. Initial voltage is 300. Then it is now you can see that both the voltage are nearly constant and maintained at 400 volt. And the most important thing I told you that the PMSG, there is a low voltage ride through capability. And the company, the government of any government want that the turbines should stay connected, and they should contribute to grid in case of disturbance such as voltage drain. So if you see some now also some videos of General Electric, they have just shown this low voltage ride through capability. So in they have very nicely made that video. So sometime you can see that if one of the relay just by some this created some fault, and completely how it is going lowering the voltage from one bus to another bus to another, and it transmit to also the transmission wires, and it is also affecting to generating side also. And when it is affecting the low voltage in the generating side, then what are the different kind of protection it gives, that it takes care, and then how it is under that condition also wind turbine is connected. They have a small video, sometime you can look into that. I don't know where the link also, I don't know, but sometime I was saying. So wind farm should generate like conventional power plant, supplying active reactive power for frequency and voltage recovery immediately after the fault occurs. So if you see the grid code, you see here at time 0, there is a fault, and the voltage is nearly 15% voltage. So this still 15% of the voltage, your generator should be connected with the grid. And when it is, you can see that at 150, around 200, the 400 millisecond. Till that time, there is a very low voltage of 15. And this then slowly it brings to the nearly the normal stage. Here we have simulated for this converter for the Spanish grid code. You can see that Spanish grid code is around 20 percent of the voltage. Okay, voltage drop, and Germany grid code is around 15%. And these two grid code we applied to this converter system, where the grid voltage dropped to 15%, and from the 15% again this profile was applied, and accordingly this you can see here. This is our grid voltage. Grid voltage was full and it was supplying around 400 volt. And suddenly there is a fault, and where there are voltage right through. Okay, so when there is a fault, so completely you can see that voltage come down, again it increase like that. So you can see here, when there is a fault, so suddenly there is a dynamic current change. You can see here, dynamic current change, and in the middle after steady state it reached, because low voltage, so current slowly increase, and when this is increasing, you can see that the current also slowly increasing like a linear, and like that. So if you see, this is a voltage sag we have applied. When there is a voltage sag, then automatically you can see that this is the DC link voltage, which comes down to 450, 750, and then oscillating. Now, if you see here, as the voltage come down, you can see the modulation index rises. So as the voltage come down, how you can, output voltage is V output is nothing but M times the modulation index times VDC. Okay, and they depend on the whether it is square wave or pulsating or that pi by 4 or that things you can add in. But if you see this MA, or the modulation index times the DC link voltage. So this DC link voltage comes down, you can see that the modulation index rises actually. So as you can see that the voltage at the output, they try to maintain the output voltage. That is why the companies, the government is asking the companies that the grid, the turbine should be connected during fault condition also with the grid. That means if it is connected there, what you need to do? You need to do only the change the controller structure. So during that period, the controller must give, and this is what the modulation index rises. So when if you see here, the current, you can see here, this is the current in the neutral current. You can see that this current is during the voltage sag, there are neutral current, and during the normal time, low current in the neutral. So if you see here DC link voltage, as soon as there is a voltage sag, the DC link voltage comes down, but it is not collapsing. You can see that is what the double, if it is a double fed induction generator, suddenly the collapse, it will collapse the voltage, because you have connected both the converter. Okay, they cannot operate simultaneously, and the second one, there are magnetizing loss. So your ride through capability, your low voltage, and here magnetizing loss, and both of them, they will create one problem, and this is why the permanent magnet synchronous generator has inherent the low voltage ride through capability. You can see that the DC-link voltage falls to 400 volt, but again it try to come back to your steady state value. And during the transient period, you can say that why this transient, this around 950 or 980 voltage is maintained for a long time, because it depends on your inertia. The factor of J is coming, inertia in the motor. If it is a small rated motor, this will quickly come down to 800 volt. If it is a very large motor, it takes, because the mechanical time constant is very large. So the steady state, that's why you need a very large time to bring to the steady state. If in this period, if there is this steady state period, like example 950 or 980 volt, and your device is rated for 800, generally we give up to 1200, but still sometime, because it may go beyond 1200 also. Okay, so that time how to bring back the system, and sometimes the system will collapse in between that also. So that is also possibility. Okay, properly, if you have not chosen the controller and not chosen the dynamic of the system, the complete system is there will be collapse. So when you see under the transient condition also, under the sec condition also, both the DC link voltage VDC1 and VDC2 are maintained balanced actually. And this you can see the during transient, this is the perfection of the controller. So when you design a perfect controller, you can see that both this DC link voltage, although it follows this DC link voltage, both the voltage are balanced under all transient conditions. And this is what the voltage. And the modulation index, you can see that when it was around 0.9 modulation index, now during the voltage seg, modulation index became nearly 1.8, 1.6 in average, 1.5 in average. So like this, if you see that the voltage comes down, then your modulation index improves, so that the output voltage can be maintained constant. So this is, you can see that this is also following the same characteristics. And here, this is the line-to-line voltage. If you, in the multi-level converter, when your modulation index is very small, so very small, less than 0.5, it behaves like a two level. Or the modulation index, you go, you can see here, it behaves like a two level. Then again, when the modulation index comes to moderate rate, so it becomes again like a three level converter output, means 5 level output you get in the line to line voltage. So these are the few investigation where I have not put the experimental result because it will take long time. So the experiments also we did. And here, this generator, in the when you have an isolated system, or especially remote power system, and there inbuilt there is a problem with the frequency, and that is why we need to have a inbuilt frequency regulation capability. So RAPS, the remote area power supply, is one of the very critical system modeling. And then we will discuss this one. Remote area power supply system are very challenging to construct, because the device is power rating. For example, you have a device which is a 50 hertz power rating, but you cannot get all the time 50 hertz. So this, what are the secondary frequency support system, we will see here. And the challenge to construct RAP system, PMSG, one of the attractive features is the high energy density. efficiency, and inbuilt low voltage ride through capability. These three are making the permanent synchronous magnet synchronous generator as one of the very famous generator for high power wind energy conversion system. So RAP system with combined with battery storage, okay, and the permanent magnet based development can be best choice, okay. So frequency regulation is, if you go to America, I was working in this project in the USA. There is a called FNet, frequency frequency monitoring network. Okay, frequency monitoring network is FNet project is a very popular project in America. So what they do, they take the data, different data from the different substations, and the data are, first thing they study two things. One is the frequency. Second one is the sag in the line. So you have a big transmission line. In India, we never monitor that transmission line, sag. Sag we never monitor till this line is broken into two parts and few people die, then only we do that. Whereas in America, I was working some time for 1 2 months in that project. So what we will do, we will from GPS we will get data that every day how much this that seg travel in every day. Then they calculate in a week. So when they will come to the tolerance range, then they will remove that line and they will put another line. So that between two poles there is a conductor, and that conductor seg they try to study. And second one, they study from each by using GPS control, and that time they use it to measure the different frequencies. So every frequency in the substation they use it to measure and try to, if there is some frequency deviation, they try to control so that the frequency can be improved. So this is also the similar kind of the analysis that when the frequency control is maintained when both the power generation and consumption are balanced. Okay, so when they are balanced, the frequency can be within the specified limit. And when you use power electronics and generators, where generator doesn't have, for example, in your classical generation system, you have AGC, automatic generation control, where that controls that one. And second one, you have flywheel as a storage element where you feed the power during the peak hour. So like that, it is also this also a significant reduction of power system frequency regulation capability. And a PMSG-based wind generator system cannot supply a certain amount of spinning reserve in response to the frequency disturbance, since they always operate in the maximum MPPT mode. So this is one of the things that in conventional generating system you have a spinning reserve, where here you do not have that one. And how to operate this? So the stored kinetic energy of the entire rotor is sufficient to support the power system frequency during transient process. In some area, total amount of installed capability of the wind generator is much larger than the local load need. So then the extra available wind power can fully preserve, harness to enhance the frequency support performance. So supplementary controllers are needed to be well designed. And then inertial response primary frequency regulation as well as wind power reserve is needed. So when we see this frequency regulation, There are auxiliary frequency controls in DFIG system we have. Inertial control support, droop control, and deloaded control also possible, and secondary frequency control associated with supervisory wind farm control also available. A coordinated frequency regulation we use in the DFIG. Whereas GLA structure, it is a simple drive train and an illuminate of DC excitation because PMSG and high power density. So that is what this is the configuration of the permanent magnet synchronous generator, where you can control the pitch angle here and the connected to permanent magnet and connected to back-to-back converter system connecting to the grid. Okay. And there are coordinate frequency controls are also available, where this gives the signal to your W reference. Okay. And if there is some frequent deviation, then there is some comparators which compares we feed to this. And then you have a grid side converter control, that is the same way. So this is the structure of DV5G, how they are controlled by using the rotor speed control and inertia control. But we are interested, so the rotor speed control, you can see that there is a the deviation in the frequency, then you have this. This is the complete control structure for the rotor side control. And now we want to actually coordinated control of this frequency. You can see that the actual frequency you give, and then your storage power, then accordingly you can develop, and then this reference frequency and extra frequency is compared and pass through this mode 1. You can see here is if F is greater than 59.8, this is 60 hertz system, and F is less than 59.8 hertz. Okay. So this is what the coordinated frequency control. This is the flow chart that how to control this system, and then we use this mathematical. This one we have a wind turbine, a PMSG connected through 2-level converter and one. And there are a bidirectional converter which is connected to the BSS, okay, storage system. And there is a dummy load which is connected, because sometimes if you see here, you produce more rather than using it in the irrigation pump in the load. If the irrigation pump is not working, but you are producing this wind turbine. So what you will do, if the battery is fully charged, so you need some kind of dummy loads, or it will consume that power. And then we have a 3-level, and we connect it through a LC filter to the irrigation pump. And this is one of the RAP system, okay, a remote area power system, okay. So this is one of these one. And the wind turbine model, I think all of you know it, what is the wind turbine modeling of the thing. And this is the direct torque control which we have implemented here, because you can ask this direct torque control. Direct torque control is it will actually has a fast dynamic and no coordinate transform. So very simple control structure. Also you can have very simple hardware as well as the controller also will be very low cost simple controller you can use for controlling this. And this part is controlled separately. This is called the generator side control, is a direct torque control. And you can see that T generator is minus 3/2P. So this minus indicates that you are generator retarding torque. Okay. And the load side converter is controlled by using VYF control, because generally in the irrigation pump, if you go and see in the village, till now also many place, they use the star delta starter, and after that they use the now they are using VYF control because nowadays the this controller has come very low cost. Okay, so you know that there are different. It is a reference speed and then limiter, then the speed, and then you find out the switching logic and turn on. So this is the filter design for this and converter circuit. So if you see, this is the filter design parameter. Okay, and so these are the parameter we found out. So if you see here, the DC link voltage, you can see that DC link voltage is maintained constant. But it is constant, but there is a fluctuation. Okay, that is. And this is the DC bus voltage. Okay, when there is a step change, you change some load suddenly. So there is step change, you can see that voltage deep down. Again, they go to the steady state. Okay, the voltage. And then the DC bus voltage, when the load is removed, suddenly large amount of load you remove, you can see that DC voltage rise actually initially, then come to the steady state. And this is the starter current, electromagnetic torque, and uh, torque, and then this is the speed. So you can see that when there is a sudden load or sudden torque you apply, then your speed reduces. But because it is a closed loop, it reaches to the steady state. So this is the experimental setup where we designed, and then this experimental setup is you can see that here is our this is our irrigation load, which is connected here and is stable, and this generator is producing. Then we are feeding to the converters. You can see here converters, and these are the current and voltage sensors, and top one is current and voltage sensor for the VYF control. So this is what the. So if you see here, the dynamic response, you can see here there is a speed. Okay, this one, and because of this one, when the motor is static, so it takes care of the inertia. Inertia during that period, the frequency is very small, and that is the that time the frequency maybe this frequency you cannot go to 50 hertz frequency. So that time the generating period, your deloaded period, the frequency will drop, and because of the secondary frequency support, we can see that the frequency reaches to the steady state. So here we have conclusion. We have discussed the PMSC and the DTC and web, and typical laboratory also experimentation we did. Okay, so if this I discussed a little about the wind turbine. So if you have any questions or comment till this point, we will discuss. Else, I will continue for solar.
So, announcement to the participants. Do you have any query related to the presentation till now being delivered? You can put it down in the chat box. Sir, I feel participants don't have any query right now.
Okay.
So please, if you wish, you can continue. Yes.
So today we will discuss the You must have seen in the conventional way, we put a solar plant, then you have a DC converter. From DC converter, you have a common DC link, then you have a voltage source inverter, then you connect to the grid with the transformer or without transformer. So this is the conventional method. Everywhere followed that one. So here in this one, we discuss a non-conventional type of like current source inverter. You know, voltage source inverter, because that is a very well established switching algorithms are available, and it is simple to control. It can have a bidirectional power flow. So that is why that converter was very popular. So that is why VSI is very simple and grid connected. It is also has the low voltage is there. Also, it has short circuit capabilities, and then we use it to connect. But here, if you see here, this one, where current source. Current source, why? Generally, current source inverters are very stable. Especially, I will give an example. I was working in the paper mill, JK Bond paper, where JK paper mill in Odisha, Raigada, is a place. So initially, after my BTech, I was working. So I was in the maintenance. So I remember there are two huge machines, and I never thought that the industry they use synchronous motors, and they had this current source inverter, and one was cycloconverter feeding. And then I was just astonished there that even though sometimes voltage fluctuation comes, the motor speed maintains constant. Why it is very important? Because the current source, because when the speed is not deviated by voltage fluctuation, okay, so that means if little deviation, you will see the quality of the paper will go down. So that is why you require such a robust system. So the current source inverter is robust, okay, because it is also unidirectional devices are needed, and there are many additional things are required when you want to develop this one. And then you have a PV array, and then you have a large inductor where it will behave like a constant current source, and then it will control this one. So you can see that this bidirectional switch, because now unidirectional switch, you can use the IGT MOSFET, sorry, you can use the thyristors, okay, they are self-commutating, and they can be used. They are semi-self-commutating. But self-commutating devices are now cheaper, and you can use it. Here we can see that the IGBT has internal diode inherently, and IGBT in series with a diode, and this feed. So this became a unidirectional power switch or unidirectional converter. So this is the unidirectional switch. Okay. So this three-phase is exactly the LC filter. So this is the control block diagram. Here, you do not require a DC-DC stage to maintain the MPPT. Here, automatically MPPT is maintained by measuring this DC, the PV and IDC. And this actual DC is compared here. And then the PI controller, then calculation of the modulation block, and then it is connected to the modulation signal, and it is the, and you get from three-phase PLL. PLL I will not discuss because it takes a lot of time. You can see just locking the frequency, okay, input and output frequency. Sometime in the village, they used to remove rice from the straws, rice straws and rice. So that time they will put a two, three bull, they will rotate and find out. And this bullet, the 4 or 5, you can say that 4 or 5 bulls, they will rotate and they will yield the crop. So that time, if you see, some bulls they will go here and there, and then after half or like that, you just beat them, and they will synchronize after some time. So that is exactly what the PLL does actually. So that is what the angle information, other information it will give to your controller circuit, and that you can build it. So there are also DC link voltage, you can write like this, and average DC link voltage, and these are the mathematics. I am not going to discuss this mathematics. You know better than this mathematics what I have written. So the plant model is a very simple model you can design, and this plant model is VPV. You can this simple model you can do, and the by equalizing the power, input power is equal to output power, you can find out the relationship here, PAC and PDC, and then you design the body plot. You can by compensating system, and you can see here nowadays this is very simple. You can get any type of system. आधा घंटे के बाद. So this plant system is there, and the closed loop system is stable or not, you can easily do. So what is the constraint in CSI? It is not like VSI. So there are a lot of problems in CSI control. So one control is that two switch, one must be top inverter top leg, one switch should be on, and bottom leg should be on. Anytime two switch must be on, because there is a constant current. It's like a forcing function. Forcing function means it is like a if you have seen a river. When sometime I remember in the Burla Engineering College, I was once I visited during my BTech. I was in NIT Raulkela, and we visited to Burla one night. We visited there, and the morning there was a big siren. There is a Hirakud Dam, okay, big drain where they produce nearly 450 megawatt power. So at that dam there is a power channel actually one, and in that power channel they opened in the early morning. There was a heavy siren and opened that channel. When there are 4 or 5 channels are there. One channel they opened, and I was seeing that there was no water, but suddenly water raised to around more than 15 feet water, and that much of water suddenly no time it improved, and that is our current is that exactly like that power. That channel. So if you stop in the middle, it will devastate here and there. That's why we do voltage control. We do high voltage transmission, rather low voltage, low current, high voltage transmission, because voltage breaking is easier than current breaking. Okay, so it is like a river. So that is why you need that at any amount of time you should not break the current. If you break, a complete converter will burn or it will damage. So that is why one converter upper leg must be on and lower leg must be on. And if there are no path, then suddenly it will damage also the switches. And if there are more than 2 switches are on, for example, upper one leg is on and lower two switch are on. So that means you see you have a two path. The two paths will try to send the current, the injected current waveform. If you see the output waveform current, line current, are not defined because there will be undesired and uncharacteristic harmony. If the harmonics are uncharacteristic, for example, 2.5 the order harmonic. Okay, so those type of harmony you cannot characterize. So these are the uncharacteristic harmonic will be produced. That is why the switching logic realization must be very systematic. And you can see that there are 6 active switches and 3 null switches, which produces zero current, and 6 active switches. And each switch is conduct for 60, 60, 120-degree conduction mode. You can see that switch S1, first two, is conducting for 120 degree, and S3 is conducting 120 degree, S5 is conducting 120 degree, S2 is conducting 120 degree, and this way you should properly coordinate this one for switching this. Then we have a PWM thing, and this you decouple and and this is, you can see that this is this in the DC link in the VSI. You can see that your reference was the voltage signal, where here reference is the current signal, and this current signal is it is constant, and you can see that this is also trying to track. And the voltage, grid voltage and current are unity power factor, and they are also sinusoidal in phase. And the modulation index, you can see that initially, because it is a current fed converter, so you can see there are chattering in the initial stage. Initial stage means during transient wave, as soon as you turn on, there is a chattering because it is a current fed. So there are a lot of chattering here. And after that, you can see that in the steady state, and there is no chattering. That is why ASCI, those converter, auxiliary commutated, auxiliary switch commutated thyristor, okay, and basically CSI. So that there what we use to also we use what we use the capacitors between two lines, okay, in the converter structure. Why? Because to just to remove the chattering. Second one, to remove the spikes, okay. So that is what here the modulation index, and you can see this is the DC the voltage, and this type of structure you use to get the charging or DC link current in the VSI. Then you can see that this is a output current, which is 120 degree phase apart, balanced one, and this is your voltage and current. They are in phase, and there are some ripple in the current. So you can. So this is also your THD, which is 4.21%, and this is our filter, inductor and capacitor voltage, and this is our the capacitor current, filter current in phase A. And I want to test the robustness of my PLL. So I deviated the frequency from 50 Hz to 48 Hz. You can see that the PLL is tracking within 1.5 cycle. Within a cycle, you can see that it is tracking the frequency or locking the frequency input and out. So this is the what we have a this is feeding to the grid as well as the local load. This is the experimental setup what we built here, and these are the experimental results that how this is this this converter work, and this is the conclusion. So this then this is all about the CSI and the complete control we design, and there are a lot of things need to be done here in the CSI fed PV system. And this just a few days back, this is one of the paper which is actually came in industrial applications, IEEE transition. So this is for improving the the power quality by using resonance as well as concurrent control theory. This is like a hysteresis current control, but this is well known to everyone. Okay, VSI feeding to the grid by using LCL filter. This is well known. So what is unknown to us? Unknown to us is the how it behaves when you have three kind of frequencies. One is your resonant frequency, another one switching frequency, another one is your sampling frequency. These three frequency plays an important role in this circuit, and that is you can see that this structure is well known structure. But when you model this one, and we model this complete PV system, and this PV system, these are the modeling. I am not going in detail, and I will share these slides where you can see this one. Okay, you can go through this one, and it is available. So I want to speak this fundamental, what is important in this one. So in this one, the important is that when you model this one by using state space model or kind of the transfer function, so that you will do. I know that that is not a big deal. So when you have a different kind of switching technique, so when we use, when you have a, for example here, you see one is single band and then one is a double band. So the single band, the output voltage, you can see it is like a bipolar, whereas the double band, it is like a unipolar. So unipolar, bipolar, I think you must have studied, where that is, there are a lot of advantages in the unipolar structure as compared to bipolar. Some advantage, but the DC link utilization is nearly the same. Okay, so we use here P plus resonant. So why we use the resonant control and P plus resonant when we use? So if you see the tracking error of the current, because you are comparing two current, actual current and the reference current. And current is not purely sinusoidal, current is like a ripple and coming. And these two current, when you subtract, the output current will have some kind of, the structure which is, or the output current structure is like a, nearly the tracking error is fluctuating in nature. So when there is a fluctuation, means there is a positive part and negative part. You can easily use this type of controller, that P plus resonant controller. Where resonant controller is only the problem is the tuning of this frequency, resonant frequency. And this, when you use this controller and you implement this one, the generating S, and these are the switching logic based on this hysteresis current control logic, and you can develop the logic gate. By using logic gate, we developed this one, and this is the modified double band hysteresis current controller. You can see that the output voltage is here like a unipolar structure, and these are the given here, and this complete system is simulated here, experimental, and we used the Opal RT OP570, and then current and voltage sensors are here, DC link capacitor, grid. and LCL filter. Local load also you can see here, lot of bulbs are connected. These are we have applied a local load. And this is implemented. Here you can see that in the modified the hysteresis current control, you can see that in the hysteresis current control, when there is a zero crossing, current rate crosses zero, the frequency is very high. Whereas when this is zero crossing, frequency is very low in the modifier. And that is what this is very effective. And the second one, you see, we try to suddenly change the reference current. You can reflect, you can see here, the current is completely, always it is sinusoidal in phase, and as soon as there is a reference current change, so it also affects here. And similarly, here there is also in the both method, it is compared. Okay. Now these are the hardware result, where you can see here we have a transient current. Okay, the reference suddenly changed, and the reference current, and they are maintaining always unit power factor, and then they are feeding to the grid. So there are you can see here, this is a comparative table that there are many things need to be discussed. The first thing is the PWM technique the proposed the hysteresis were controlled. You can see that the switching frequency zero crossing is not required. There are many things need to be studied actually, and this shows that there are many things need to be studied. And this is the few references. And anyway, I think what is time now? It is around 50. We have nearly 10 minutes. So I cannot discuss this concurrent current control. So I'll go directly to our implementation. Okay, this also I cannot control now. And this also I cannot present today, and this one, but I can discuss, yes. So this is our microgrid design and installation. Okay, this was our first project which we implement in Tennessee Technological University, Kukui. So Dr. Gao asked us to go and we install ourselves. This is a 12 kilowatt solar plant. And you see, this is a small micro DC microgrid. It was supplying this power to these the three houses are there. You can see here 1, 2, and 3. They are the stores actually of that institute, that university. And we supplied this power from here, but we put this one, and but it was a very haphazard. Quickly we did it. And but what are the problem? There was no wind clearance. In 2010, 2009, we installed this one. And again, I went in 2014 that this structure is completely devastating. So because there is no wind clearance, no optimum angle, no structural stability, and no grass-free land. Grasses are growing and so on. So then next project is in Nashville. It is in Schneider Electric. Okay. So this is you can see here, Schneider Electric. Our project was to supply this. You can see I have marked here this smart device based on IoT. So we designed this IoT device. But this design is very perfect. Minimal wind clearance, optimum angle for summer, and structural stability, and there is a wind clearance you can see here clearly, and it is a grass-free land. It is in Tennessee, Nashville. And this project we did in our IIT Patna campus. So we can see that complete structure we designed, and it is actually 200 kilometer per hour wind also it can sustain, and perfect structural stability rooftop. So you can see here, this is our control room, and this is our control room. And then you can see that there are also the stars which is given, you can change it during different, the different during winter and summer you can change. So, so that is what there is a power quality monitoring at light load. Light load, the power quality you can see here in this CRO, the at light load, this second one megawatt solar plant at IIT Patna. It is a distributed solar plant and 1 megawatt, and it is completely communication control, data logging, everything is available here, and smart metering also. And it is not a storage, there is a locally generated and utilized. Okay, so all are implemented here. There are few projects we implemented in different villages, and in the Araria district of Bihar, around 40 unit in the 15 village of 1.2 kilowatt package we have installed. And then we used it in the Toipur is a one village. This is the Toipur village. In that village there is no power. So we installed around 10 kilowatt power for this one, and with diesel generator also. Okay, you can see this is the variable speed diesel generator which is connected here, and variable speed you can read actually this. There are a lot of advantages. That's what this generator. And then the battery storage system you can see here. This is battery storage. I am standing here, and then variable DG and 50 houses load are supplied. And a few microgrid projects, last microgrid project we designed and installed by Reserve Construction at Port Blair Air Force Station. So I have not given entire complete but our project is in this region. Okay, where I am showing this one arrow, that is the place where we installed 1 megawatt. But the problem was due to the soft soil, your structure is unstable. Second one, the sand particle strikes on the solar panel, and trenching also there are a lot of problem in earthing, and dynamic balancing. And this is the complete. You can see that this is the complete design of the Air Force Station 1 megawatt power plant, and this is the just fencing and the inverter room, and these are the panels. So I am not. I will not share this thing because it is Air Force Station. So this is the cabling diagram, and then earthing pit. You can see there are many earthing pit. And why this is required? It is very important because the soil is soft. So the earthing pit, if one earthing pit is failed, other earthing pit will give you the support. That's why these are all the earthing pit are connected. And this is the solar microgrid project at IIT Patna, which we developed with the sponsor of MHRD. And this is for smart IoT, smart grid, and smart building, these three. And then this is our another imprint project where you can see that there are two. One is a horizontal wind turbine, vertical axis wind turbine, and we have a DC solar tree. The three are connected together. And this is the complete unit. And you can see that wind, solar, controller, and smart load. So this is the, you can change also, and there are some videos. And also you work on the micro hydro turbines. Okay, this is the micro hydro turbines where we are installing. This is the hydro turbine, and anyway, so this is the print project, and this is my contact. Thank you very much. If you have any questions or comment.
So over to the participants. If you have any query, any doubt, anything related to this, you can ask.
Sir, where is this micro hydro plant is installed in IIT Patna or
No,
somewhere else?
no. We installed in Tennessee Technological University. Okay.
Okay, okay, okay.
So I tried
And
to get this generator, but till now it is we are not able to find it. Okay. But there here it is a river. So here we put, and this is this cable is the channel. So you just connect it. It is 1 kilowatt. Okay, micro hydro, and you have a storage power
so
plant.
Ganga River is basically very close.
Huh?
Ganga River is basically flowing through the Patna.
Yeah, we don't have such a huge big turbine is required for that. It is a small storage
Yeah,
power plant.
yeah. So that's why I thought that you might have channelized
No, I want to purchase
and
one.
installed it.
I want to purchase one, and surely I want to purchase that.
And what is the size of the microgrid system which you have installed in IIT Patna, sir?
There is one microgrid around 10 kilowatt. That is that we use for our experiment, as well as a few loads are connected. And there is a distributed microgrid which is 1 megawatt. Okay. And there is a DC microgrid which is nearly 650 watt. So
Is there any query from the
So
participant
this
side?
was the
Hello,
uh,
sir. So you have installed 10 kilowatt solar plant in villages of, you said in
no,
Patna and
this is in
in.
Toypur village. Toypur.
Okay. So, sir, what was the social issues that you faced after installing that solar plant? Were there any
There
social
are a
issues?
lot of social issues. First day, we went there for putting the installation. Okay, and I gave this is a generator. We connect, and there was a solar plant was not installed. And from generator, we need to give power supply to the villagers. So first thing what they did, I gave the our car. I told who was the mukhya. Mukhya means he the chief of that village. So I this was
Yes, sir. Yes.
sponsored by G and Tata Power. Okay. So when we put that one, and I sent him to bring 20-liter petrol, this fellow left around morning 9 o'clock, visited all his relatives home till we are there till night 9 o'clock. There is no power. Our students are fearful that sir snake will bite everything, and we had only mobile power also finished by that time, and we were in that dark place sitting together till 8 o'clock. That is the first social issue. And I told, where you have gone? It is only 5 kilometer distance that petrol pump, and you came here now in the night 9 o'clock. He told, no, sir, I visited all my relatives' house and came. Oh, like that. So their villagers, they do not know, and our people also, they don't want to stay. So till now it is working, and we put IoT based communication system. And whenever there is a problem, our technicians go and get them. That is the problem. Or else these village people sometimes they break the solar panel. The kids they play there. That is there. So you cannot stop that. So these kids, they were, you can see here, this kid, they are throwing the stone. So instead of that, I gave them a nice, you can see the orange. I had orange. I told, please take the orange and go home. They were throwing stone to the solar panel. Okay. So that is there. So you cannot avoid it.
Sir, so anything that could be done to avoid such situations,
Such
to tackle those issues?
situation in the village that you need to make them understand that this is for your purpose. And we should make them responsible. That's why the skill development, and if you appoint them, the village people will be appointed there. Then that will be very nicely controlled. That's why village skill development program need to be started, which they can maintain their own plant. If anything is required beyond that, they will contact. And they can control because they know these boys, whether his name is Prakash or Pinky, whatever, they will call and they will tell, hey, don't do that, they will do. Okay, somebody must own it. That is more.
Yes, yes. Thank you, sir. Thank you.
Okay. So if you don't have question, then we can stop here. And if any question, I am putting in the chat box.
So do
If you
we
have
have any other question to be asked? Participant side?
So I am giving my email address. You can in the chat box. If you have any questions or comment, you can send.
Yes, sir. Yes, sir. I don't find any question from the participant side. So I feel there is no query from their side right now. And sir, it was really a wonderful lecture, wonderful experience, both from and whatever you gave a glimpse of your work to us, the research paper. So the various key points that I gathered from your lecture was that the power processing topologies applied to PMSG, its working and merits. Then about the simulation results that you illustrated about grid phase voltage and phase current, voltage sag, low voltage right through, and then discussion about the remote area power supply system, its challenges that are faced during its construction, and the objective behind the frequency control. So it was an extensive work of yours that you have delivered to us. So with this, I, on behalf of Kanati family, give you a really heartfelt vote of thanks that you spent your busiest time today gracing this FDP. Today, we had the opportunity to hear your thoughts, your work, and definitely this is going to encourage us in our future activities. Sir, we really hope to see you again for such expert talks again. Once again, thank you, sir.
Thank you so much. Namaskar. Namaskar. Jogesh sir, thank you.
Thank you, sir. Thank you.
Thank you, madam.
Yeah.
Thank you very much. Thank you.
So, an announcement to the participants that your attendance link has been posted in the Google Meet chat box. You can mark your attendance for today's session 1, and the next session will commence at 11:30 a.m. So till then, you can mark your attendance and be ready. And since the day 1, you have been cooperating with us. So a very huge thank you to all the participants.